So my talk is probably a bit more number theoretic than geometric compared to other talks. So I apologize in advance for any logs I say in this talk. So this work is joint with several people, Jillian Eddy, Matt Lipman, who's here, Daniel Martin, and Nico Trapani. It started in an RAU at UC Davis and advanced a lot after that. I will also say that although this talk is quite number theoretic in nature, these Markoff triples I'll be talking about throughout the talk have interpretations that are more geometric. And while I won't mention that too much, even if you are more of a geometer, hopefully these are of some interest to you. Okay, so what are Markoff triples? They are solutions, non-zero integer solutions to this equation there. So you can, let's see, does this work? Yeah. You can actually change this to minus 3 x1, x2, x3. It's another equation, but the solutions to these two equations are related, and everything I say today about this also applies to that equation as well. Okay, so here's one such triple, 3, 3, 3. If you plug it in, it works out. And how do you find more solutions? Well, here's going to be the idea. So let's say you know a triple ABC, like 3, 3, 3. If you fix two of the coordinates, B and C, and plug those into the equation, you'll get this quadratic equation that you can solve for x1. Now, one of those solutions is going to be A. And the other solution is, well, it's the other root to this quadratic equation. The sum of these two solutions should be BC there, the coordinate in front of x1. So you get A plus the other solution, A prime, is equal to BC. So if you know that A, B, and C make a triple, then BC minus A is this other A prime, is also forms a triple with B and C. Okay? So that gives you a nice way to generate some triples. And in fact, it's known that it'll generate all such positive, so non-negative triples. So what you do is, well, okay, so first of all, I should say, what we did was we fixed B and C and solved for A, but there's no reason why you shouldn't fix A and C and solve for B, or A and B and solve for C. So you get these three sort of transformations, which sends ABC to BC minus ABC. That's the one we considered. But then these two others as well. And if you look at the group generated by these three, they're involutions, actually. If you square them, it's the identity. And you act by that group on 3, 3, 3, you'll get all of the non-negative Markoff triples. And I want to emphasize the fact that these are nonlinear, because this makes this, at least from my point of view, a very different kind of problem than many of the other problems of this flavor that number theorists consider. So it's very common to look like at the orbit of a subgroup of GLNZ or something like that, acting on some n tuple, and study the arithmetic of that. But this is a completely different beast. And a lot of the geometric and algebraic tools that we have for this other kind of problem just simply don't exist here. So it's a much more difficult sort of Diophantine equation to consider. Okay. So we have this thing called the Markoff tree, which is basically the representation of what I just said. Here, so we start at 3, 3, 3, we apply R3, we get 3, 3, 6, and so on. You'll notice I didn't include here the branches where you go from 3, 3, 3 to via R2 and R1. That's just because you'll get, again, 3, 3, 6, but permuted there. And then all those branches will be the same as this stuff, but with some permutations. And same with this 3, 3, 6, I only included R2 instead of R2 and R1, and that's because R1 will, again, instead of getting 3, 15, 6, you'll get 15, 3, 6, and it'll be some permutation of everything we have there. So I did not include those in this picture. You kind of see how, as you walk out along this tree, the triples are growing, and not only are they, so what's happening is, each time you apply one of these involutions here, you fix two of the coordinates. Here you fix 3 and 39. And that third one that changes, it grows, is the kind of the pattern here. And these were first studied by Andrei Markoff, as far as we know, in his master's thesis in 1879. And he looked at these in an application to rational approximation of real numbers. And I won't get into too much in that, but maybe that's already one hint of a relationship to geometry. Usually, continued fractions classically come from SL2Z. And you can realize it as something happening in the hyperbolic plane. So this is somehow related to all that. Okay, so here's some interesting questions, interesting from my point of view. So in this tree here, right, if you look at the Markoff numbers, again, like the number 15, it occurs there, and it occurs there, and it occurs there again. So it occurs a bunch of times. But really, it's, I think of it in this tree as just occurring right there. It's born there in the sense of it came from the first time we saw it after this involution R2 was applied. And then here the reason we have 15 is just because that coordinate is being fixed. And there that coordinate is still being fixed. So it isn't like, for example, here we have this 1299. Like maybe somewhere way out here for some reason we also get 1299. And the question is there a unique place where any Markoff number is born? Or could there be more than such place? So as stated here, does any Markoff number occur as the largest number in some Markoff triple up to permutation and sign change? Yeah, so this is not known, but it is conjectured that, sorry, what's going on here? It's conjectured that this does not happen, so there's a unique triple in which a Markoff number occurs as the largest number up to permutation and sign change. This is called the uniqueness conjecture. Are there infinitely many prime Markoff numbers? So as a number theorist, that's what I'm drawn to, is question about primes. And again, well, we think yes, but we do not know. Sometimes in these kind of questions, if you can't answer something about primes, maybe you can answer about R almost primes. So R almost prime numbers are numbers with at most R prime factors, counting with multiplicity. And unfortunately, though, you ask this question about R almost primes, we also don't know if there's infinitely many R almost prime Markoff numbers for fixed R. And we can't say anything about sort of how many less sub x are there. Okay, well, I've told you a bunch of stuff that we don't know, so I'll give you one thing that we know about, which is how many Markoff numbers are there less than x? And this answer was answered by Zagier in the late 80s. It is some constant times log x squared. So this is sort of, it's not a reason for why it's hard to answer these questions about primes, but it's sort of all part of the same thing, which is that Markoff numbers are very sparse. So when you look at these subgroups I mentioned of GL and Z acting on some triple, and you ask a similar question, usually if your group is nice and we can work with it, you get something like a power of x. And here we're getting a power of log x, which is considerably sparser. So it's very hard to say, well, this thing we know about the integers and distribution of primes there also happens like for this very sparse set. Okay, so it's almost similar in flavor to, like, I don't know, if you look at Fibonacci numbers, and in fact Fibonacci numbers come up in Markoff numbers, and you ask like something about primes and Fibonacci numbers. We don't know anything about that really, or very little, and it's a similar sort of difficulty. Okay, so I want to talk about how we approach these questions. Are there questions so far, though? Yeah?
Is there something known about statistics of Markoff numbers, like Erdős-Katz theorem or something like that?
Oh, no. No. But I will talk about Erdős-Katz theorem in a little bit. Yeah, we don't know anything. We do know there's one thing that we know at this point, which is very sort of unsatisfying. There are infinitely many Markoff numbers that are composite. And there's, in fact, for any R, if you look at R almost prime numbers, it makes up a very small proportion. But that's what you would expect anyway. So, yeah. Other questions?
Yeah, if the Markoff uniqueness conjecture was known, would that imply Zagier's results? I mean, I guess what I'm asking is that Zagier's result really looks like the question of the growth in the number of curves on a torus.
Yeah, yeah. It is actually kind of exactly where it comes from. Yeah, yeah. But I don't. Yeah, I mean, if the uniqueness thing was known, I'm not sure you would get anything else in Zagier, but maybe you could interpret Zagier's result in a certain way. Yeah. Yeah. Okay. All right. I'll move on. So how do you start answering these kind of questions about like primes? Well, a key player is going to be something called the Markoff mod P graph, or the mod P Markoff graph. I wrote it here. And here's the reason. The reason is that mostly, at least as an analytic number theorist, when I think about counting primes or something like that, I like to think about using a sieve. So I take my numbers and I say, okay, I want to sieve out all the numbers with small divisors. And the way I'm going to do that is I'm going to say, okay, I know the total number of Markoff numbers that I actually know, or say the total number of Markoff triples if I want to work with triples. And I want to sieve out all the ones where, say, some maximal coordinate is divisible by 2, and then by 3, throw back in the ones divisible by 6. So this inclusion-exclusion type principle. And to get a handle on how many there are where the maximal coordinate is divisible by 2 or by 3, etc., I have to consider this equation, but mod p. In fact, I'd rather consider mod a square free integer d, but we'll start with mod p. Okay, so what are these Markoff mod p graphs? You take the Markoff equation and you look for solutions in fp cubed, so mod p. And those solutions are going to be, going to represent the vertices of my graph. How many are there? Roughly p squared. So it's p squared plus or minus 3p, depending on whether p is 1 or 3 mod 4. If you're 1, it's plus 3p. And if you're 3, it's minus 3p. Let's see. And we're going to take two vertices and connect them by an edge. If you can go from one vertex to another via one of these involutions, R1, R2, or R3. OK. So we're going to call this graph GP. So it's very tempting to say, oh, well, this graph is just this tree, but mod p, right? But that's not true necessarily, because what could happen is you could take, maybe there's a solution to your Markoff equation mod p, and there is no triple in Z, which is that thing mod p. So there's no way to lift your mod p thing to something in there, in which case the vertices in my GP graph are not even just these things mod p. So we'd like for that to be true. We'd like for this Markoff mod p graph to be exactly this tree mod p. And basically saying that these are the same two things is to say that the graph GP is connected. Okay? So it is coming exactly from this tree and reducing mod p. Okay. So, yeah.
What happens if p equals 3?
If p equals 3, this is what happens if p equals 3. I see what you mean. I must have misspoken. This should be, I guess for p should be 12. Yeah, so here, yeah, you have some, see, it's, or, hold on a second. 8 non, yeah, 8 is not 0, that's right. So, what did I say, p squared? Oh, you know what, I think, you're very observant. I think this might actually just be true for primes greater than or equal to 5. So anyway, but that's very observant. But here is the mod 3 graph, okay? So you have in this particular case this nice kind of cubical structure. You don't always have this nice symmetry. So this here is the mod 7 graph. I didn't label the vertices because there's a lot of them. But yeah, you can come up with these really nice images of these graphs for small primes anyway. But certainly that's not a way to start proving that all Markoff mod P graphs are connected, which is really what we want. Okay, so what do we know about Markoff mod P graphs? So in his PhD thesis, Arthur Berrigar conjectured that GP is connected for all primes P. As far as I know, there wasn't anything that happened until about, well, the mid-2010s. So Breguin, Gerbert, Starnak worked on this problem. Breguin is now no longer alive. I should say I think they made their first announcement of their results in the early 2010s. But at this point, if you look what's publicly available, there's nothing published. They have an announcement of their results, some of which there's no paper at all available. This is not to say that they have, this is not a slight against them. I'm not trying to say they haven't proven it, it's just not available. The stuff I'm going to mention here, though, is all in a paper that's on arXiv, but again, it's not published yet. So if you look at that paper on arXiv, there may be some typos and things that you have to sort through. So, but anyway, in 2016, they showed that GP is connected for all but a zero density subset of the primes. And so as far as what this density is, that is not something that you can easily tell from their paper. The key is, very roughly, that p squared minus 1 should not be too smooth, meaning it shouldn't have a lot of small prime factors. And again, that's not a rigorous statement. There's a rigorous sort of statement that needs to be satisfied by the prime p for their results to actually imply the connectivity. They also show that if you take any epsilon greater than 0, you take p large enough, the graph GP will be made up of at least one big connected component of the graph, which I'll call CP, and I'll refer to this component throughout the talk, so you have this big connected component and everything else is of size at most p to the epsilon. And furthermore, they showed that for any connected component, it must be of size at least log p to the 1/3. Okay. So actually, Konyagan, Makarchev, Sparlinsky, and Vugin in 2019 improved this exponent of 1/3 there in the log p to 7/9. And they also sort of specified a little bit more about how this epsilon looks like they were able to give an upper bound of 2/3 plus little o of 1 as p goes to infinity. Okay, well, then there was this sort of huge result in 2020 by William Chen, which is a consequence of an algebra geometric result that William Chen proved. This is a paper in the Annals. And he showed that actually any connected component in the Markoff mod P graph has to be divisible by P in size.
Can I ask you a question?
Yes.
Why is the epsilon less than 2/3 an improvement?
It's not an improvement. That's not an improvement. It's like a specification of sort of like, like maybe well, I don't know. To me, it's just sort of saying like, for Breguin, Gerbert, and Starnak, they're saying for any epsilon, you can take a p large enough, blah, blah, blah. This is saying like, for epsilon less than 2/3, I don't know. I guess it's the same thing. Yeah, I guess it's the same thing in some sense, but it's.
Yeah, it's weaker, right?
Well, yeah, but I think that they kind of investigate this method of Breguin, Gerbert, and Starnak in a little bit more depth, and they're able to come up with these more precise statements. I don't know. No, you're right, but it's. Yeah. So if you want, just focus on the 1/3 improvement to 7/9. Yeah. Okay. Well, so this result of Chen's you can take that and combine it with this statement from Bergen, Gerbert, and Starnack about epsilon to show that GP is connected for all but finally many p. Because take epsilon, I don't know, to be 0.8 or something like that. That's something less than 1. This shows that at some point for p large enough, GP is going to have this huge connected component and everything else is a size less than p to the 0.8. But if your size is less than p to the 0.8, you're not going to be divisible by p, unless you're size 0. So you can't possibly have anything outside this connected component at that point. What point that is a different question. But for all but finally many primes p, GP is connected. An improvement over this first thing that for all but a 0 density subset of the primes, GP is connected. So what I want to talk about in this talk is I want to get an upper bound on the largest prime p for which GP is maybe not connected, and generally sort of what happens for the smaller primes as well. Okay, so for that, basically the only way anybody has right now to walk around this Markoff mod p graph is the strategy that Bergen, Gerbert, and Starnack used to prove the connectivity. Here's the idea. Here's what they do. So they actually work with a graph, like if you look at their paper, that's a little bit different from GP. It has the same vertices, but the edges are defined instead of by the ri's. They're defined by these rho i's, which are you take ri plus 1 and compose it with the transposition of the coordinates I plus 1 and I plus 2. How to think of this is rho I is still fixing the ith coordinate. And then for the other two, you're basically, like let's say we're looking at rho 1, you're basically fixing that first coordinate, and then you're applying R1 and R2 and R3, one after the other. Really? That's what this transposition of the vertices does. The reason they consider this, well, there's various reasons. But one nice thing is if you think of it that way, if you look at rho 1, say, of x2, x3, then, so x1 is fixed, and what's happening with x2, x3 is you're acting by this matrix in SL2 of p. Now, there's an x1 in there, so like you haven't suddenly made your nonlinear group into a linear group. Because for every triple x1, x2, x3, this will be some different subgroup of SL2 of p, and you can't just take all of them and somehow glue them together into one subgroup of SL2 or something like that. So it's not how it works, but this is nice because you can then use, you can then come up with some nice statements that are coming from this linear group. So then the idea is the following. If you start with x1, x2, x3, let's say this one right here is some triple. And you apply this rho 1 over and over again. So look at the group generated by rho 1. It'll have some finite order. It will actually, the order of this matrix in SL2 of p will always divide p plus or minus 1 unless it is of order p or 2p. I'm kind of going to ignore those cases throughout this talk because for those are special cases that we know are actually going to be in the big connected component. But so you apply this rho 1 over and over again to x1, x2, x3, and you get this black orbit of triples, where the size is the order of this matrix. And then at every single point, you have two other orbits, one corresponding to rho 2 at that point, and one corresponding to rho 3 at that point. Okay, so at each point, rho 1, rho 2, and rho 3 are well, rho 1 is the same, but rho 2 and rho 3 are different. And you walk around this orbit, and your hope is, as you walk, to find that one of these other orbits is actually larger in size than the black one. Once you find one such thing, like maybe right here, this blue one is larger, is larger order, you jump to that one, and then you walk around that one and do the same thing, growing the order of the associated rho I all the time until you get to an orbit of maximal size, where maximal is going to be for us p plus or minus 1. This is a rough outline of their strategy, and I'll give you more details as we go on. But so in their paper, they have this opening, middle game, and end game. You can tell they like to play chess. The opening I find to be not a very good description of what's going on. It's not really the opening. It's what you take care of in the end, in some sense. But fine. So the idea is that if you're in the middle game, so if your order of your row I is between, like if you take a triple and the order is between p to the epsilon and p to the half plus delta. Now epsilon and delta actually depend on p, so it's a little bit misleading. It isn't like some fixed constant, and I'll talk more about that later. Then you can play this game that I just talked about, where you walk along, you find something of larger order, you go to that, you walk along, you find something of larger order, and so on. Once you hit the end game, where your order is quite large, you can actually go directly from your orbit to something of maximal order. You don't have to keep walking up, up, up. You just go straight to a maximal order guy within your orbit. Then you have this opening, which there's nothing to do here as far as like this walking thing goes. But I'll say how they handle that once I give more details. So basically, I mean, this can come out of their representation of the graph that they consider. By the way, I didn't say this, but the graph that they consider is actually, it's like if you can prove that's connected, then your original Markoff mod P graph is connected and vice versa. So I'm going to actually talk throughout the rest of this talk about the actual graph GP that we defined. So here's a parametrization of Markoff triples, mod P. So if you have a triple where A is not 0, and it's also not plus or minus 2, this plus or minus 2 is exactly the situation where you get your row, I guess 1 in this case, has order P or 2P. So we'll ignore that case. This solves this equation if and only if you can write your triple in this way for some R and S and FP squared. Okay, so YFP squared. How does this work? Well, for example, take p equals 7 and consider this triple here, which is a triple mod 7, 4, 3, 1. You can take R to be 2 plus 4 root 5, where root 5 is, you'll take it to be some square root of 5 in FP squared, so FP adjoins square root 5, and S to be 4 minus 4 root 5. And you will get that this is 4, 3, 1. In general, how do you find sort of the R and the S given a triple? Well, so you want to solve for A congruent to R plus R inverse, mod P. Just rewrite it as a quadratic congruence, like this. Multiply through by R, and that's going to be a quadratic equation. So you're either going to find a solution in FP or in a degree 2 extension. The discriminant is A squared minus 4. So if this is has a root in FP, your R is going to be in FP, and if not, you have to go to FP squared. Okay, hopefully that makes sense. Now, if you look at the orbit of that triple, the way we wrote it, under the group generated by R2 and R3, so this guy is fixed, and then these two coordinates are going to look like this. The K, the 2K plus 1 and the 2K, that depends sort of how many R2s and R3s you've taken so far. And I mean, this is just where you're fixing the first coordinate. You can do the same thing for fixing the other two coordinates. How many triples are there in this orbit? It's going to be the multiplicative order of R in FP squared star. Okay, so for some notation, if you have a triple x1, x2, x3, and FP cubed, and xi is rho plus rho inverse in this same way, we are going to say the order of that coordinate, mod p, is the multiplicative order of rho. And the order of the whole triple, with a capital O, is the largest of these orders. Okay, so what we're doing in the strategy of Bergan, Garman, Starnek is we're walking along the orbit trying to grow this capital order. Here. Specifically, you're in the middle game. If your order is large enough, you have a triple of larger order in one of these orbits acting on A, B, and C. Okay? So you walk along these orbits, increasing your order until you get to a triple of order roughly p to the half. So what is this roughly p to the half? And Bergan, Garman, and Starnek's paper, because they really don't care about like precisely saying like exactly for what primes p we're connected. They just want to show it's connected for all but a zero density subset. They just write p to the half plus delta. We made this precise. It's exactly this point. So the tau here is the number of divisors of p plus or minus 1, and the phi is the Euler-Tosche function. So the number of integers less than p plus or minus 1 relatively prime to p plus or minus 1. So if you're taking, what do you take plus or minus 1, that's basically depends on whether or not you're looking at some row I where the order divides p plus 1 or p minus 1. Okay, so that's p to the half plus delta. Here's your p to the half, and the rest is the plus delta piece. Okay, so if your order is larger than that, then you're automatically connected to this wonderful large connected component of the graph. So what about the opening? So basically, the middle game and end game say that if your triples of large enough order, they're connected to each other. All triples of large enough order are connected to each other. So for the opening, you basically ask, well, how many triples potentially do not have large enough order, so you can't play the middle game and end game, and hence we can't show, they may not be in CP. The idea is to show that there's very few of them, and there's less of them than the lower bound we have for the number of triples we have in any connected component. So for Brigand-Gabbard-Sarnak, that was this power of log thing, but we now know by result of Wu-Chen that the number of these bad triples not connected to CP must be divisible by P. We actually show that it must be divisible by 4P. It's not that any connected component inside is divisible by 4P. It's just if you look at all these bad connected components together, the number should be divisible by 4P. You could improve that to 12P if you could show that the triple 333, for example, is connected to the large connected component, but that's not known. Although, like for the first 10,000 primes we checked, and it is. So if we can show that the number of these bad triples is strictly less than 4P, then you get that GP is connected. So that's what you do in the opening. Okay, so that's the rough strategy. Maybe I'll stop here for questions before I go on to what we can get from this. Okay. So remember we had this parametrization of the orbit. So I'm going to put up this lemma, which at first seems like, what on earth are you talking about here? So say you have this R of order t greater than 2. Okay, so this R over here is of order t. So if you look at the orbit, you get this orbit you get here. There's going to be t points in that orbit. And the question that I'd like to ask is, so if you look at, this says number of congruence classes of n mod t. If you look at n going from 1 to n, or these powers here basically, we're going to allow ourselves to go up to n. So for how many of these triples, when I look at one of these two coordinates, so this is exactly what these two coordinates are, except instead of 2k or 2k plus or minus 1, I've put in an n there. How many of those have order that divides d? So I'm going to say why that's interesting in a second, but this is an upper bound on that number. What we're ultimately interested in is the case where d divides p plus or minus 1 and d is less than t. Why are we interested in that? Because when we're doing this game of going up, raising the orders, we'd like to say that in this orbit, we can find some point whose order is greater than t, right? So what we'll do to do that is we'll count the number of points that have order less than t, or maybe less than or equal to t. And then we will say, well, if that number is less than t, which is the total number of points in the orbit, then there should be at least one that has an order greater than t. So we want to get an upper bound on the number of triples that don't grow in order, and hopefully say we have some left over where the order does grow. So that's why this is interesting to us. And specifically,
so
yes?
Statement, how do you quantify for S? What is S in the statement?
S.
S is a
Oh, this S. So, right. we're talking about a specific triple that we start with, which is parameterized with this R and S. Yeah. Yeah. Yeah, thanks. Okay, so the idea is, where does this bound come from? What you're doing is you're counting the number of solutions to the following things. So here is exactly this expression, except I replaced R to the n by x. So basically, I think of R to the n as something where you take it to the tth power and you get 1. Right, we just want an upper bound, so this is fine. And then I want this to be equal to y plus y inverse, where y to the d equals 1. So the order of y divides d. So literally, we're looking for solutions where y is coming from the subgroup of fp star of order d, and x is coming from the subgroup of order t. And this is a kind of problem that falls into a more general result by Carvalha and Zanier, which is sort of algebra geometric in flavor. And we're able to take that and just get these 3/2, a 6, and the 4 based off on this particular curve we're looking at here. Okay, so that's something we'll use in a moment. It's, again, going to be applied in order to see sort of when is it that we can play the middle game. Here's a proposition that is actually our first criterion for checking whether a Markov mod P graph is connected or not. It's the first criterion that was ever published. And what it's saying is the following thing. So if you have a prime P, where if you look at all the divisors of P plus or minus 1, and no divisor satisfies one of these two inequalities, then your GP is connected. So what is this? This TD is the number of divisors of P minus 1 and P plus 1 less than D. So tau D sub of n is, did I write that down? Yeah, it's the number of divisors of n less than or equal to D. So you have these two inequalities. And basically for any P, you can just go on your computer and try to check this, whether or not this is true. And if you get that it's true, then your graph, so no such divisor satisfies this, then your graph is connected. If you get that it's not true, then you can't conclude anything. Let me point out, for those of you that you know about Erdős-Katz and so on, this should be pretty trivially, usually, not satisfied. Usually. Because, so this TD, coming from tau D of P minus 1 plus tau D of P plus 1, Erdős-Katz says that at some point you expect that most numbers, n, have log n divisors. And clearly, a power of log n is not going to be greater than the square root of P. So there's not going to be a divisor that's greater than that and less than that, trivially. And same here. You're not going to get this happening. But the tricky thing is, first of all, we're not working with all numbers n. We're working with these P plus or minus 1s. Second of all, well, when does Erdős-Katz kick in enough for this to actually work? And third of all, what about the things for which Erdős-Katz is not satisfied? So, okay, but this, I mean, just looking at this from considering Erdős-Katz, you should say, oh, this is already saying you should be expecting connectivity. And the basic idea is that if this is satisfied, and specifically if this is satisfied, then this is too small. Let me show you a sketch of the proof, just because it's sort of, I mean, seeing these inequalities without any explanation just seems kind of icky. So here's the idea. So suppose your graph is not connected. Then take, among all those things that are not in this big connected component, take a triple of largest possible order among all those triples. So there's going to be such a thing. Let's say D is the maximal order among triples that are not in this big connected component. And take a triple of that order, and we'll just assume that that order is attained in the first coordinate. That's not losing any generality or such a triple will exist. Okay, well, what happens to the second and third coordinates in the orbit of R2 and R3 acting on this triple we're fixing? Well, first of all, they will have order less than or equal to D, because they're also not in the big connected component, since they're connected to the guy that's not in the connected component. So by the maximality of D, this should be true. And D prime divides P plus or minus 1, because as I said, the ones of order P and 2P, they're automatically connected to the big connected component. And there's exactly D choices of exponent in this parametrization of the orbit. And I'm just going to remind you of this lemma here really quick, because we're going to use it in a second. So here's what I'm going to do now. So the total number of triples in my orbit is D, in the orbit of R1, R2, R3 acting on this thing, on this triple that we're fixing. Here's an upper bound on it. For any divisor D prime less than or equal to D, divisor of P plus or minus 1, the total number of triples where that second and third coordinate might have order dividing D prime is this. So that's an upper bound corresponding to D prime. Sum over all those D primes. Clearly that should be greater than or equal to D. Okay, because this is an upper bound on the number of things in the orbit. Then take a really rough upper bound on this. There's TD summons here. And for each one, D prime is less than D. So I'm just going to less than or equal to D. So I'm going to replace D prime with D, and I get this bound. And the nice thing about this is now I can get some kind of inequality statements on D from saying that D is less than that, about this bad potential order D. Okay, so if the max is 4D squared over P, you look at that thing that I just had, and you get D is greater than P over 6TD. So D is greater than P over 6TD, but it can't be too large, because if it's too large, the end game kicks in. So that's where this little piece, why that's there. Now, if max of these two things is the first guy, then you solve for D and you get D is less than this 81T D cubed over 4. So you just need to show that D is greater than this to complete the proof of the theorem. That involves the following thing. So if you look at the number of distinct A in FP, excluding this plus or minus 2, for which this order is at most D prime over 2, it divides D, that's at most D prime over 2. The reason is that, well, there are D possible R's that you can put in here, and these two things are the same, so you divide by 2. Okay, so what you can then say is, all right, so I have D prime over 2 choices for A, D prime over 2 choices for B, for 2 divisors less than D of P plus or minus 1. And then once I choose my A and B, there's at most 2 solutions for C, because I get a quadratic equation. The funny thing is, so a student of mine, Colby Brown, has been looking at this, and actually, usually you don't have any solutions. Like, this is a way big overestimate. Like, if you just take some A and some B, finding a C is not at all guaranteed. So you have that the number of Markoff triples of order at most D is this much. So given how we chose D, which is that it's an order of this bad triple, this is the total number of things of order less than or equal to D, or an upper bound on that. If that is less than 4P, then according to Chen, you don't have any triples of order less than or equal to D that are not in the main connected component. So when we assumed that this triple of order D was not in the main connected component, so you must have 4P is less than that. And that is where we get this inequality for D, which is this thing right here. So you can think of this, this as the opening plus middle game, and this is the middle game plus end game. Okay. So from this, we can conclude already that P is connected for all primes P greater than 10 to the 532. How do we do that? Yeah, it's pretty bad, but. So the whole thing, there's like tau floating around everywhere. And there's a bunch of different upper bounds you can play around with, but here's an upper bound by Nicola on tau of n. And what that's going to give you is, well, our TD that appears in those inequalities, it's this thing, so it's upper bound by roughly this. And then using this, you can show, you can check that this inequality, so remember there was a situation where like your divisor, your prime P is bad in the sense that GP might not be connected if there's a divisor D that is greater than this but less than that. So that's not going to happen if this inequality is true. So, and that is going to be true for P greater than 10 to the 532. There's that other inequality in there, but that second inequality, you can, using the same approach, show it's already not satisfied for P greater than 10 to the 141. So that is not going to be the main thing, main obstacle here. Okay, so that's the first bound. How can you improve on this bound? Well, here's a observation, like a natural observation. What we're doing, remember, when we're proving this proposition and using this lemma of ours, is we're counting the number of solutions in a subgroup of FP star of order, of order dividing P plus or minus 1. To this equation we had, right? We had this equation here, and we were looking at these solutions where these y's had to be in a subgroup of order D. Now what happens if you, like remember we have this D less than, then we have a sum over all divisors of P plus or minus 1. What if you look at two divisors in that sum which divide each other? So if you have T and T prime, which are less than D, which are divisors, and T divides T prime, then what you're doing is first you're counting all of the solutions in this subgroup of order T prime, and then you're counting solutions in this subgroup of order T, which is contained in the subgroup of order T prime, so you already counted them. So you're doing an overcount. So rather than looking at all divisors of P plus or minus 1, you should be looking at a kind of set of maximal divisors. And that's where we're going to introduce this notion, which appears not to have been studied before. If you have a positive integer m and some number x, less than or equal to n usually, but this is fine if it's greater than n. A positive divisor of n is maximal with respect to x if first of all d is less than or equal to x. And there's no other divisor d prime of n where d prime is divisible by d and d prime is also less than or equal to x. So like if you look at all maximal divisors of 12 with respect to 7, say, that would be 6 and 4. Because 2, 3, and 1 won't count because they divide either 4 or 6. If you look at all maximal divisors with respect to 12, well, that's just 12. So it changes depending on x. But it gets rid of this issue if you consider these maximal divisors, which we're going to call m sub x of n, instead of all of the divisors. Instead of these sets, tau d, I guess I call them, or td. Okay, so if we replace this td with the md, we get the same exact statement, except everywhere we had td, we have now this md, which is the number of maximal divisors of p minus 1 and p plus 1 with respect to d. Okay. So this criterion actually helps us, like if you actually use this criterion on your computer, it helps you find a lot more graphs GP which are connected for smaller primes P. And it allows us to lower that bound of 10 to the, what was it, 500 something, down a bit to 10 to the 392, roughly, 3 times 10 to the 392. So I'll say first, what do we know about these maximal divisors? We have this theorem here, which is for any epsilon greater than 0. If you have alpha in this interval, you get this about m sub n to the alpha of n. If you compare this to this right here, which is this bound of Nicholas, it isn't that different. But it turns out that, first of all, it turns out that if you look at the numbers less than 10 to the 532, which is what we started with in our first corollary there, that are particularly bad in the sense of having particularly large m sub n to the alpha, we're able to improve our bound to this here. So I don't want to get into too much exactly how this works, but it's like you basically reduce all numbers between 10 to the 392 and 10 to the 532 to just a subset of sort of ones where this maximal divisors might be large, and you work with those. So it's not a great improvement as far as any sort of, it's not like we can suddenly now check all the primes less than 10 to the 392, or we couldn't check it for 10 to the 532, but it's an improvement, right? So
it's 140 orders of magnitude.
It is, yeah. I mean, it is, but in practice, it doesn't get us any closer to showing all primes are connected somehow. So some comments about that. To do better than that bound, you're going to need some significant new ideas. So we know that there are primes as large as this weird thing, which, what is that? So first of all, it's roughly like 10 to the 392. And what this 863 hashtag, or whatever you pronounce it like, means now is all the product of all the primes less than 863. This is all the primes less than 53 and so on. So it's a pretty big number. And we know that for this number, our criterion will neither prove nor disprove connectivity. And there are tons of numbers that we can list for which our criterion doesn't give us anything. And like you're not going to be able to, I don't think you're going to be able to just kind of fine tune like what set of divisors you're looking at more and more to really get a wonderfully better bound. Another note is our criterion works best for large primes. Like if you look at primes less than 1 million, you can basically not handle almost any primes. I'll show you some data on that later as well. And as far as our criterion goes, 10 to the 31 is roughly where the Erdős-Katz theorem takes over, and using maximal divisors over, like as far as the actual, like just testing connectivity and using that first proposition as I showed you versus the theorem with the TD versus the MD, that's roughly where like you don't really need the MD anymore. You could get away just using tau because Erdős-Katz kind of kicks in. So that's interesting. All right, so some data. We've tested this up to 10 to the 90. It just kind of, I didn't want to show you 100% more tables with just 100% in it. But what this is this over here. So this is looking at primes between 10 to the 8th and 10 to the 9th. It's taking 10,000 random primes from that interval. We can't look at all, like especially as we get larger, it's just, there's too many primes there, we can't look at all of them. But we can select 10,000 random primes, and I can tell you how if you'd like. And we're getting here like 38.12% of them satisfy criterion, so GP is connected, and so on. And you see at some point you just get all 100%. Does that mean that all primes give you between like 10 to the 22 and 10 to the 23 give you GPs connected? No. We can list in each one of these intervals primes for which we don't know connectivity based on our criterion, but it just means that you expect most of them to be connected. Okay, so what about smaller primes, right? I said like our criterion doesn't really work below 1 million roughly, and it's not that great for those beginning, like 10 to the 8th and to the 9th type primes. So De Corsi, Ireland, and Lee, their paper actually focuses not just on connectivity, but also on expansion of these graphs. So I didn't mention this, but I should say that sort of the chef's kiss results about these Markoff graphs mod P would be not just that they're connected, but that as a family they make up an expander family. This is conjectured to be true by Bergan-Gabbard-Sarnak. If you don't know what that is, think of it this way. So let's say we know all these graphs are connected. Then we expect in each one, if you start at any vertex and take a random walk around these graphs, let's say your random walk is of length n. For n large enough, you're expecting the probability of ending up in any one given vertex to be the same, roughly the same for all the vertices. And for expander graphs, this equidistribution happens very quickly if you look at all the graphs mod P. Sort of if you compare the error between equidistribution and what your actual probability is, that should be getting small quickly for expander graphs. And that's the kind of thing that De Courcy-Arlen and Lee are mostly focusing on in their paper. But they also show along the way that GP is connected for all primes less than 3,000. So my student Colby Brown, who's really like a computer scientist combined with a mathematician, like he really knows his coding, he's been able to extend this to primes less than like 10 to the 8th. So a huge push, and using the kind of ideas that I was talking about in this talk. And he's developing his code to push this code further. We were also looking with him at this question, which, well, some people think, okay, this method of walking around the graph given by Bergan-Gabbard-Sarnak, maybe that's not the most natural way to think about connectivity in this graphs and not the best way to walk around them. So maybe there's some large primes for which this method just won't work. Like you will be able to find some triples of small order where you literally just can't walk up in orders to the large connected component. It actually seems like, it seems like the answer to this question is probably no. In fact, even if you have a triple of small order, not only can you walk up eventually to something of large order, you most of the time can find in the orbit of that triple something that's of maximal order. So, so probably not. But yeah, so that's pretty much all I had to say. So thank you.
Thank you for that lovely talk. Are there any questions? And if so, let me bring the microphone to you.
So if you know that the graph is connected mod P, do you know it's connected mod P square?
Yes, I think it's not obvious, but I think that is actually known, but it is nowhere in, like you can't find it publicly. But I think Bergan-Gabbard-Sarnak.
It's known to
yes,
you.
Yes,
to
I think
Peter,
they have.
yeah. So it's periodically minimal?
I don't think you know all the powers. I think you specifically know it for P squared. You also you do know it for products of different primes.
No, but I was asking periodically.
No, I think it's known for P squared, but I don't think it's known for other powers.
So you don't have a classification of compact invariant subsets
no.
on the periodics?
No.
Okay.
Any other questions?
Just a quick idle question. There's lots of other equations that are of degree 2 in each variable besides the Markov surface. I'm wondering if you or other people have investigated
yes. So I do have some work with Joe Silverman and Matt Lippman and Austin Tran where we look at Markov-like equations in the sense that like the symmetries that you get are very similar. And we have considered those. It doesn't seem like the story there is, you can't just sort of take the Bergan-Gabbard-Sarnak method and translate it into there. However, Bergan-Gabbard-Sarnak did consider sort of the situation where you set this equation equal to not only 0, but also other values of k. And I think that's one of these papers that they haven't published. But yes, it hasn't been considered, but there's not like a lot, at least of this flavor.
So you say you don't know the answer to what you told us today.
Wait, what was the question?
If you take the Markov family
Yeah,
XYZ, you don't know the answer to what
the answer to what?
I mean, you are looking for.
Oh, no.
is the graph connected?
Yes, it is known to, so Bergang and Sarnak claim to have shown that.
For, I mean,
For
what
any,
type of term are you adding?
For any
Are you adding
k,
a constant or are you adding a linear term?
oh, no, just for k equals an integer is what they consider, yeah.
And in that case, you know it's
Yes.
connected for most
Yeah,
primes
I
or
mean,
for all
yeah,
large enough primes.
It isn't yet publicly available, but supposedly they have proven this. Yeah. But I don't think it's been proven in any other instance. Like adding a linear thing, no.
And if you change P a little bit, so if I fix P large, I don't know whether the graph is connected, but I'm allowed to move to the previous prime or the next prime, and you want to prove that you have connectivity.
Mm-hmm.
Can you do that? Because the dynamics change a lot if you move a little bit P. You know.
Yes. I don't know what is, basically, well, if you just use these kind of arguments, the question is what happens to P plus 1 and P minus 1? Like, is it true that if you go from one prime to the next prime, that suddenly here you have like a really smooth P plus 1 or P minus 1, and here you don't? I don't know. Yeah, I don't know. That seems like a hard question. Yeah, I think that's a hard question.
Yes, thanks for the talk. I wanted to add a comment and a small suggestion for discussing. So recently, Maury, Genoux, and Ovsienko, they suggested a Q analog of the rational number based on the constant fraction expansion. And this naturally works also for real numbers. And their machinery also suggests a Q analog for Markoff numbers. And it turns out that the Q analog of the uniqueness conjecture is true with this way of generalizing the Markoff number. So I don't know if there is a Q analog mod P Markoff number to work with, but this is something we can discuss.
Yeah, sounds interesting.
Was there another question? Okay, let's thank our speaker again.